Imagine tossing a pebble into a still pond. What happens? Ripples, right? These ripples spread out from where the pebble fell in. They are disturbances in the water's surface. Gravitational waves are similar. They are ripples, but not in water. They are ripples in space-time itself. Space-time is the fabric of our universe. It's what gives us the dimensions of space and time. Massive objects like stars and black holes warp space-time. When these objects move around, they create waves. These waves are called gravitational waves. These waves travel at the speed of light. They carry information about the objects that created them. They tell us about the events that happened long ago in the universe's history. That's why they are so important for cosmology. They are like messengers from the distant past. Gravitational waves were first predicted by Albert Einstein. He described them in his theory of general relativity. However, it took a long time to actually detect them. This is because they are extremely weak. They interact very weakly with matter, making them very difficult to detect. The first direct detection of gravitational waves happened in 2015. This was a groundbreaking discovery. It confirmed Einstein's theory and opened a new window to study the universe. Now, we can use gravitational waves to learn about objects and events that are otherwise invisible to us. Think back to the very beginning of our universe, the Big Bang. It was an incredibly hot and dense state. Everything in the universe as we know it was concentrated into a single point. Then the universe expanded rapidly. This expansion is called inflation. During inflation, the universe expanded at an extraordinary rate. This rapid expansion stretched space-time itself. It's believed that this stretching created ripples. These ripples are the primordial gravitational waves. Primordial gravitational waves are special. They are different from the waves created by stars and black holes. They were created in the first fraction of a second after the Big Bang. They carry information about the universe's earliest moments. These waves have been traveling through the universe ever since. They are faint whispers from the Big Bang. By studying them, we can learn about the conditions in the very early universe. Imagine finding a message in a bottle. This message has traveled across a vast ocean. It can tell you about a distant land and time. That's what primordial gravitational waves are like. They are messages from the beginning of time. They can tell us about the universe's birth and evolution. Detecting gravitational waves is a technological marvel. It requires incredible precision and sensitivity. Imagine trying to hear a whisper in a crowded room. That's how difficult it is to detect these faint ripples in space-time. Scientists use sophisticated instruments called interferometers to detect gravitational waves. LIGO and Virgo are two examples of these detectors. They are giant L-shaped structures with arms that stretch for kilometers. A laser beam is split and sent down each arm of the interferometer. The beams are reflected back by mirrors at the end of each arm. When a gravitational wave passes through the detector, it stretches and squeezes the arms. This changes the distance the laser beams travel. This tiny change in distance creates a pattern in the light. Scientists analyze this pattern to identify the presence of a gravitational wave. It's like looking for a tiny ripple in a vast ocean of light. However, detecting primordial gravitational waves is even harder. These waves have been stretched out over billions of years. This makes them incredibly faint and difficult to distinguish from noise. It's like trying to hear a pin drop in the middle of a hurricane. The universe is full of mysteries. Two of the biggest mysteries are dark matter and dark energy. We can't see them directly, but we know they exist because of their effects on the universe. Dark matter is a mysterious substance that holds galaxies together. It doesn't interact with light, so we can't see it. However, we can infer its presence from the way it affects the rotation of galaxies. Dark energy is even more mysterious. It's a force that is causing the expansion of the universe to accelerate. We know very little about its nature or origin. Primordial gravitational waves could hold the key to unlocking the secrets of dark matter and dark energy. These waves can tell us about the conditions in the very early universe. This is when dark matter and dark energy played a crucial role in shaping the universe as we know it. For example, the strength and pattern of primordial gravitational waves can tell us about the amount of dark matter and dark energy present in the early universe. This information can help us refine our understanding of these mysterious components of the cosmos. Section 5. A Cosmic Symphony. The interplay of gravitational waves and the cosmic microwave background. The cosmic microwave background, or CMB, is a faint afterglow of the Big Bang. It's a snapshot of the universe when it was just 380,000 years old. The CMB is a treasure trove of information about the early universe. Primordial gravitational waves left their mark on the CMB. They created a subtle pattern in the polarization of the CMB light. Polarization refers to the direction in which light waves vibrate. Imagine throwing a stone into a pond. The ripples from the stone will create patterns on the surface of the water. Similarly, primordial gravitational waves created patterns in the polarization of the CMB. Scientists are searching for these patterns. They use specialized telescopes to measure the polarization of the CMB with incredible precision. Detecting these patterns would provide direct evidence for the existence of primordial gravitational waves. The CMB and primordial gravitational waves are like two instruments playing a cosmic symphony. By studying them together, we can learn about the universe's earliest moments and its evolution over billions of years. Section 6. The Elusive Whispers of Creation. Challenges in detecting primordial gravitational waves. Detecting primordial gravitational waves is a monumental task. These waves are incredibly faint, and their signals are easily drowned out by noise from other sources. It's like trying to hear a whisper from across the universe. One of the biggest challenges is separating the signal of primordial gravitational waves from other sources of noise. This noise can come from astrophysical sources, such as radio waves from distant galaxies, or from instrumental noise in the detectors themselves. Another challenge is the sheer sensitivity required to detect these faint waves. Imagine trying to measure the width of a human hair from thousands of miles away. That's the level of precision required to detect primordial gravitational waves. Despite these challenges, scientists are optimistic about the prospects of detecting primordial gravitational waves. They are developing new technologies and techniques to improve the sensitivity of detectors and filter out noise. The quest to hear these faint whispers of creation continues. Section 7. Predicting the Unseen. Theoretical models of primordial gravitational waves. Theoretical physicists play a crucial role in the search for primordial gravitational waves. They develop models that predict the properties of these waves based on our understanding of the early universe. These models provide a roadmap for experimentalists, guiding their search for these elusive signals. There are many different models that predict the strength and frequency of primordial gravitational waves. These models are based on different theories about the physics of the early universe, such as inflation and string theory. Some models predict that primordial gravitational waves should be relatively strong and easily detectable by current or future instruments. Other models predict much weaker signals that would require next-generation detectors with even greater sensitivity. These theoretical models provide a framework for interpreting the data from gravitational wave detectors. By comparing the observed data to the predictions of different models, scientists can learn about the physics that governed the universe's earliest moments. Section 8. Pushing the boundaries, advancements, and future directions in gravitational wave astronomy. The field of gravitational wave astronomy is rapidly evolving. New technologies and techniques are constantly being developed to improve the sensitivity of detectors and expand our ability to observe the universe through gravitational waves. One promising avenue of research is the development of space-based gravitational wave detectors. These detectors would be free from the seismic noise and atmospheric disturbances that limit ground-based detectors. This would allow them to detect even fainter gravitational waves from the early universe. Another area of active research is the development of new data analysis techniques. These techniques are essential for extracting faint gravitational wave signals from the noisy data collected by detectors. Machine learning and artificial intelligence are playing an increasingly important role in this effort. As technology advances, we can expect to see even more exciting discoveries in the field of gravitational wave astronomy. These discoveries will continue to revolutionize our understanding of the universe and its evolution. Section 9. A new window to the universe. The enduring quest to understand our cosmic origins. The study of primordial gravitational waves is a testament to human curiosity and ingenuity. It's a quest to understand our cosmic origins and the fundamental laws that govern the universe. By listening to the faint whispers of the Big Bang, we are opening a new window to the universe. This window allows us to probe the earliest moments of creation and explore realms of physics beyond our current understanding. The detection of primordial gravitational waves would be a landmark achievement in cosmology. It would provide direct evidence for the theory of inflation and shed light on the universe's most profound mysteries. The quest to understand the universe is a journey without end. As we continue to explore the cosmos through gravitational waves and other means, we can expect to make even more awe-inspiring discoveries that will deepen our appreciation for the wonders of the universe and our place within it.